Today is going to be 61-2, and we're going to take a look at the factor and remainder theorem. So today's objective, we're going to discuss the remainder theorem and discuss the factor theorem. Now the remainder theorem is a concept that involves us being able to look at our polynomials in a different manner. So now that we know how to divide a polynomial, we're going to focus on learning ways to describe it, gather some information, and actually be able to manipulate that polynomial. And so that first concept is going to be the remainder theorem. And it says that suppose P is a polynomial of degree at least 1. Remember, we talked about that. We like this n being greater than or equal to 1. And C is a real number. Then P of x is divided by x minus c, and the remainder is P of c. Now, it doesn't have to be greater than or equal to 1, but we're just saying that this theorem only applies in that situation where it's greater than or equal to 1. So it says when P of x is divided by x minus c, the remainder is P of c. Now, it's saying that the factor being divided by that is the same as evaluating by that value c. Those are same things. So let's take a look at that. Let's take a look at the implication from that theorem. So here's a scenario. I have a polynomial divided by x minus c, and I have my same polynomial, but what is it going to look like if I evaluate from that c? Well, if I divide, bring down the 1, multiply, add, my remainder is going to be 0. Well, what if I evaluate? So I get negative 4 squared plus 7 times negative 4 plus 12. I get 16 minus 28 plus 12. Negative 12 plus 12, I get 0. My remainder there is 0. They are the same. And the remainder theorem states that they're the same. Now, if you're not convinced, let's try what if I divide by x plus 5? Bring down the 1, multiply, add. Well, that's going to be the same thing as if I evaluate. So I'm going to get 25 minus 35 plus 12, negative 10 plus 12, that gives me 2. Those values are exactly the same. Now, a nice thing about the remainder theorem is this was so much quicker, right? Using that synthetic division was so much quicker than me trying to evaluate here. So that's going to be one thing that's nice about the remainder theorem is I can set it up like synthetic division and go through and work it through that way because it's a much quicker and easier process. The next is going to be the factor theorem. Now this states that suppose P is a non-zero polynomial. The real number C is a 0. That's supposed to be C. It's hiding behind there. The real number C is a 0 of P if and only if x minus c is a factor of P of x. Now, this is saying two things. Remember, if and only if means it's a two-way statement, so this is going to go both directions. So the first is going to be, we know that c is a 0 if x minus c is going to be a factor of P. So I can write the 0 as a factor. Then, if I look at it this way, if x minus c is a factor, then I can assume that it's going to be a 0. So then I can state a 0 from a factor. And then the other thing is because we know this idea that if c is a 0 of P, only if and only if x minus c is a factor, that means that I can use the 0 to divide into a polynomial written in that form of x minus c. So I can divide a polynomial with those zeros. So it's a very important theorem because this theorem allows us to break down a polynomial into a series of factors. So this first one here, it says find P of negative 2 using the remainder theorem, and then use the fact that x equals 1 is a 0 to factor the polynomial. So the first, if it's P of negative 2, I'm going to use synthetic division because it's much quicker. 2, I don't have an x squared. And so now multiply and bring it down, multiply, add. So I can say that P of negative 2 is going to equal negative 3. And then part B, it says use the fact that x equals 1 being a 0 to factor the polynomial. So that means I put 1 in the box, 2, 0, negative 5, and 3. Bring it down, multiply, add. And so because I know that it's going to be using the factor theorem, because we just determined that it is a 0, right? That's my remainder constant x squared. I can write this 0 as a factor of x minus your 0, or x minus c. And so the rest of my polynomial is here. And so I factored it. Now, a few connections between my zeros and factors and the graphs of my polynomials. All of these 5 statements are equal statements. So it says, suppose p is a polynomial function of a degree n is greater than or equal to 1. The following statements are equivalent. The real number c is a 0 of p. Also, p of c equals 0. Right? So if I evaluate c and I get 0, okay, the real number c is a 0. It's just another way of stating it. X equals c is the solution. Is the same as saying that it's a 0, which is the same that if I evaluate, I get 0. X minus c is a vector, which means that x equals c, which also means if I evaluate, if I get 0, which also means that c is going to be a 0. And then the point c0 is an x-intercept of it, which then means I can write it as a factor, which also means that it's a solution, which also means if I evaluate, I get 0, which also means that it's a 0 of the polynomial. So they're all the same statement, it's just written or expressed in a different fashion. And so just know that you might be getting these statements, and it's a good thing to be able to recognize the difference between those two statements, and for more of a contextual reasons. And it also allows you to be able to, express your statements into those different ways. Example number 2, it says you're given a polynomial and one of its zeros. Find the rest of the zeros and factor the polynomial. So because I know what one of the zeros are, like it says c equals 1, I can go ahead and I can try and break this down and factor. Remember, we learned that polynomial division is a form of factoring. So bring it down, multiply, add, multiply, add, multiply, add. So that means that because I got remainder of 0, I can express that as a factor, x minus c. And so I'm left with x squared minus 5x plus 6, because this is my remainder, constant, x, and x squared. Now this factors further. That will factor into x minus, 3 and x minus 2. And so this right here is going to be my answer. Now it says find the rest of the zeros. So that means the rest of them. So the rest of the zeros are going to be this 0 and this 0. So that's going to be 3 and 2. Example number 3. You're given a polynomial and one of its zeros. Find the rest of the zeros and factor the polynomial. So same thing. Here's my first 0. Use synthetic division. Bring down the 3. Multiply the 3's together. Well, if you have to write it off to the side to help you visualize it, always do that. Now multiply the 6 and the 2/3. So that's going to give me 4. I get 3. Once again, the 3's cancel out, and so I get 2, which gives me a 0, which is a good thing. So now I can write this as x minus 2/3, and then I get times 3x squared plus 6x plus 3. So now I have to factor that further. Well, first there's a 3 in common, so if I factor out that 3, I do get the x minus 2/3 again, but now this is going to be x squared plus 2x plus 1. And so this will factor into x plus 1 and x plus 1. And so that is going to be the factor form now. Technically, this is one of those ways to write it, but it's actually more formal than it's writing our as x minus c. When it's a fraction, it's kind of iffy, right? It's not as formal. So I can actually take this 3 and multiply it through. And if I do that, I get 3x minus 2. And so now this is the better way of writing it. And so the rest of my zeros, that's going to be -1. Last one, it says create a polynomial p which has the desired characteristics. The polynomial may be left in factored form. So it says the zeros of p are plus or minus 2 and plus or minus 1, and my leading term of p of x has to be 117x to the 4th. Well, remember, we can write it, if I know that is 0, I can write it as x minus c, so then x minus 2, x minus negative 2, x minus 1, and x minus negative 1. And then the leading term here, this is 117, and so I can write 117 out in front. And so that is an expressive way of creating the polynomial under those conditions. So this does conclude our lesson. If you guys do have any other questions, please leave them in the comments.